All right, welcome back. Day 17. So yesterday, we figured out how to use the gradient as our compass, right? It points us straight downhill to the lowest point of any valley. But what happens if the lowest point is, off limits? Today, things get interesting. We're putting up a fence. I mean, what do you do when the perfect answer, the absolute minimum, is in a place you just can't go? This is the whole game of constrained optimization. It's not just about finding the best solution, it's about finding the best possible solution when you're stuck playing by a certain set of rules. Let's stick with that mountain analogy. We've got our hiking boots on, we know how to head downhill. Easy enough. But then, bam, a fence cuts right across our path to the valley floor. We can't just hop it, we've got a new problem. Find the lowest spot we can get to without leaving the fence line. And that really gets to the heart of the difference here. Unconstrained optimization, that's like, find the lowest point in the entire universe, go anywhere, do anything. But constrained optimization is way more realistic. It's find the lowest point, but you have to stay on this specific path. It's about finding the best compromise. Okay, so why does any of this matter for AI? Well, it all comes down to one of the biggest headaches in machine learning, overfitting. You know what that is, right? It's when our model gets a little too smart for its own good. It starts memorizing the training data, noise and all. The ISLP source puts it perfectly. It starts to follow the errors or noise too closely. So these constraints we're talking about, they're the fences that keep our AI models from chasing that noise and getting totally lost. All right, so how do we actually find that sweet spot, the best place on the fence? Well, the solution is honestly beautiful. It's all about geometry. Just picture yourself again. You're the hiker, you're walking along this fence, and you're trying to find the lowest possible point. Where exactly do you stop? And here it is. The answer isn't some random point. It's this very specific, very special spot. It's the point where the contour lines of the mountain, the lines that mark constant elevation, just gently kiss the fence. That single point of contact, that tangency, that's our solution. Okay, this is the key insight, so lean in for a second. At that exact kissing point, something incredible happens. The gradient of the mountain, the direction it wants you to go, and the gradient of the fence become perfectly parallel. They line up. Think about it. If they weren't lined up, if there was any angle between them, you could just kind of scoot along the fence and get a little bit lower, right? But when they are perfectly parallel, any move you make along that fence only takes you back uphill. You're stuck. And that means you found it. You found the lowest possible point on the fence. Here's a great way to think about it that has nothing to do with mountains. Imagine you're stuck in a big circular room, and somewhere outside, there's a delicious pizza. You can smell it. Where do you stand to get as close as possible to that pizza? You'd go right up to the wall and press your face against it at the one spot where the smell gradient is pointing straight out, perpendicular to the wall. Any other spot, and you'd feel like you could slide along the wall to get a bit closer. That spot? That's our kissing point. Okay, geometry and pizza analogies are great, but how do we turn this into something a computer can actually solve? We need a tool, and that tool is called the Lagrangian. It's this brilliant piece of math that acts like a bridge, taking us from that cool visual idea to a real solvable equation. Now, it all boils down to this little equation right here. It looks simple, but it's packed with meaning. All it's saying is what we just discovered. The gradient of our function, f, that's the mountain, is just a scaled up or scaled down version of the gradient of our constraint, g. That's the fence. They're parallel. They point along the same line. That's it. And that little scaling factor, the Greek letter lambda, that's the star of the show. It's the Lagrange multiplier. You can think of it as the force of the fence. How hard is the constraint pushing back on you? Or even better, think of it as the price you're paying. It tells you exactly how much your solution gets worse for every little bit of the rule you have to follow. So the real magic trick is what we do with this. We build this awesome super equation called the Lagrangian. We basically just mash our original function and our constraint together into one big formula. And here's the crazy part. Now, all we have to do is find where the gradient of this new equation is 0, something we already know how to do. And poof, it automatically gives us the solution that respects the fence. It turns a really hard, constrained problem into a simple, unconstrained one. It's just elegant. All right, let's bring this all home. The big reveal. How is this old school math powering the AI in your phone right now?
Well, this is the secret sauce behind one of the most critical tools we have to fight overfitting. You've definitely seen it before. L2 regularization.
So next time you see this equation for the loss function, you'll know what's really going on. You're not just looking at a loss function with a penalty. You are literally looking at a Lagrangian. That lambda, it's our Lagrange multiplier just hiding in plain sight. The first part, the error, is what we want to minimize. And that second part, that's our constraint, our fence, that's forcing the model's weights to stay small and simple. Let's just map it out one-to-one. The data error, the RSS, that's our mountain. We want to get to the bottom of it. The weight penalty, that lambda term, that's our fence, keeping the weights from exploding and getting too complex. And the total loss function, that's the search for the compromise, the best possible model that balances low error with small, simple weights.
So why is this compromise so powerful? I mean, why do it at all? The ISLP source nails it. By shrinking the estimated coefficients, that's our fence at work, we massively reduce the model's variance. In plain English, that means it's way less likely to get spooked by random noise in the data. We're making a trade. We accept a tiny, tiny increase in bias in exchange for a huge improvement in how stable and reliable the model is on new data.
And honestly, that is the whole story. As the source says, this equation is all about trading off two different criteria. Regularization isn't just some random hack we tack onto our loss function. No, it's a deep, mathematically solid way to find the perfect compromise between two goals that are always fighting each other, being accurate and being simple.
But wait, there's more. This idea is so fundamental, it doesn't just stop at regularization. Once you get this concept of constrained optimization, you'll start seeing it absolutely everywhere in machine learning.
Take support vector machines, for instance. Their whole job is to find the biggest possible gap between two groups of data, but they have to do it under the constraint that their weights have a specific size. Or what about principal component analysis? It's looking for the direction of the most variance in your data, but it's constrained to only look for directions that have a length of 1. It's the same exact idea every single time, a different mountain to climb and a different fence to respect. So it turns out that building smart AI isn't really about finding the single perfect, lowest point in the universe answer. It's about finding the best compromise, given the rules of the game. This whole idea is a cornerstone of modern AI, and it really makes you think, doesn't it? Where else in our lives is the best solution not about just going downhill as fast as possible, but about finding that optimal, elegant compromise that respects the fences we have to deal with?